All right, so this is part two of module three, series and parallel AC circuits example. And I'm gonna demonstrate how to draw the impedance diagram for these two circuits or for these two examples. All right, so this is example one. So once you determine the total impedance, you are now ready to draw the impedance diagram. But the first thing you gotta have is the total impedance, which is what we calculated earlier in part one of example one. So this is just copied from everything that's above this squiggly line right here. It's just copied from above because I want to show you Z total. And so with this series combination for this network right here, in order to calculate Z total, all we had to do was just add up the impedances and and get the total impedance. So so you added up your resistor, your capacitive reactance, and your inductive reactance. And remember that your capacitive reactance is a negative value. It is a negative value. And your inductive reactance is always a positive value. All right, so once you add these up together, I did it the long way down here. So you get 50 plus negative J 17.68 ohms plus J 34.87 ohms. And you get 50 ohms plus J 17.19 ohms. So because this value right here is positive, we already know that this is going to be an inductive circuit or mostly inductive circuit because it has mostly inductive reactance. But back to the question is how we draw the impedance diagram. Well, you're gonna need this value right here, this value right here. This is kind of like your X and your Y. And then also you're going to need a magnitude, which you can use Pythagorean theorem to calculate the magnitude, the square root of these values squared. And you get 52.87. So this magnitude is always going to be a positive value because even if this was a capacitive reactance circuit, uh, and this value was negative, let's say it was negative. Once you square it, a negative times a negative turns into a positive. So therefore, the magnitude of your impedance diagram is always going to be a positive value. All right. All right. And so now the next thing you need to do, you need to calculate your angle, which you use this formula right here, the arctangent of your reactance divided by your um your resistance, and you get 18.97 degrees. And so therefore your total impedance in polar form is 52.87 at an angle of 18.97. So this is your Z total in rectangular. So you have your X, Y, and this is your impedance, your total impedance in polar form. You have a magnitude and you have an angle. And so if you were to draw this out graph it out, so this is your y-axis, this is your x-axis. And so down here would be your 50 ohms. Then you have your 17.19 ohm for your inductive reactance. Then also you have your magnitude, which is the hypotenuse of this triangle. And then you have your angle. So I'm not too particular about trying to make sure that this angle is exactly right. I'm more so concerned about making sure that it's in the right quadrant. Like for example, we know 18.97 degrees is really probably gonna be something like this right here. This is more so at if I really drew this out, this is more so at like 45-degree angle. But like I said, I'm not too concerned about making sure that the angle is exactly right. I'm more interested in you having the correct values and making sure that the triangle is pointing in the right direction. So for all inductive, mostly inductive circuits, your triangle is going to be going up. So in a capacitive circuit, your triangle will be going down. So let's say, for example, that this example was a mostly capacitive reactance circuit. So therefore, you still have your angle right here, which is 18.97. But remember, for all capacitive reactance circuits in rectangular form, this value right here is negative. So instead of going up in the positive direction, you'll be going down. So this be 17.19, and then you have your 50 right here, and then your magnitude. And don't forget your units. Oh no, this is degrees. All right, so if this was a capacitor reactant circuits, this is the orientation that you're in. Your impedance diagram should look. The impedance diagram triangle should look. It's going in this direction right here, going down, not going up. I find a lot of students make this mistake, and they always put your triangle going up, which is a common mistake because sometimes you do have capacitive reactant circuits. It's not often, but sometimes you do, and you will experience that on in this class as well on some of your exams and quizzes and homeworks. All right, just out of here. All right, so moving on to the next example. Oh, let me back up. So I did it the longhand way. Now, keep in mind, you don't have to do it the longhand way. You can simply just use your calculator to convert it from rectangular to polar, or polar to rectangular, vice versa. I'm not too concerned about making sure you know how to calculate the magnitude and angle. Although you do need to know that, because eventually you will um, be faced with a problem that will require you to calculate that. But if you want to use your calculator to convert rectangular to polar, that's fine with me. I'm not going to make you show your work for that portion right there, because I know are some calculators are equipped to doing that. And if you have the TI-36X Pro, which is a great calculator, a cheap calculator that can that does work well with complex numbers, and it can easily convert polar to rectangular and rectangular to polar. So if you don't have one of those calculators, I highly recommend getting one. They're only about 20 to 25 bucks currently, either at a local Staples or on Amazon. All right. So for this next example, so like I said, I'm not gonna go through the portion where I find the total impedance, because I've already done that in part one. And so, but for this example, I calculated Z total in polar form right here. So I'm going to go through the longhand way of converting it from polar to rectangular. The first example, I converted it from rectangular to polar. So this is how you convert it from polar to rectangular the longhand way. And like I said before, you don't have to show these steps if you are using your calculator to convert it. But just to walk through the example, this is how you do it. All right, so in polar, you're already given the magnitude, which is right here, and the angle. Right. Magnitude and the angle. So all you're trying to do is find the X and Y coordinates, or the X or the R and X coordinates, your resistance and your reactance coordinates. So, and all you really do is you take the magnitude for for your resistance, and you multiply it times the cosine of the angle. That's going to give you this value right here. And then find your reactance. You take the same magnitude, and then you multiply it times the sine of that same angle. Really, really straightforward. And so, therefore, your your impedance diagram should look like this. The impedance diagram should look like this. And so if this was a capacitive reactance circuit, this Zx would have a negative value. Because the angle on your total impedance would also have been negative. So you would have a negative value right here. And so the cosine of this angle is always going to be positive. It's always going to be a positive value because your angles that you're going to be using is always going to be from negative 90 degrees to 90 degrees. So if I drew this out right here, this is negative 90 degrees, and this is your positive 90 degrees. So you're always going to be working on this side right here. You'll never be over here. So let me draw that back. So 90, negative 90. And so no matter where you draw your angle, the cosine of it is always going to be positive. So this is positive over here. This is your negative over here. You got negative, positive, positive up here. So the cosine of this angle is always going to be a positive value. Now it's a little different for sines because you can have a sine of a negative angle, and you will get a negative value, meaning that it's, it's going to be your triangle is going to be pointing down, indicating that this is a mostly or a totally capacitive reactance circuit. If that was the case, all right. Hope that makes sense. But in this case right here, this is an inductive reactance circuit. Therefore, our triangle is pointing up. And like I said before, I'm not too concerned about making sure that is drawn exactly with respect to the actual angles and the values. I just want to make sure that you have the triangle drawn in the right direction and the values are correct. So that's all I have for part two. If you have any questions or need any clarification, please feel free to reach out to me. Thank you.